Hello, in today's lecture, we will summarize about what you have learned already in computer architecture in instructions language of the computer. As you already know, computer architecture is the science and art of selecting and interconnecting hardware components to create a computer that meets functional performance and cost goals. So what do you have in your program or in your computer? Of course, as you can see here at the upper level, you have application software, or what is which will do some specific task, or you can see it as some kind of application you download from you download somewhere to execute some game or doing some calculation. They are written in high-level language. Under the application software, you have system software here, and the system software will control all your application and the hardware. It includes two parts. The first one is compiler, which will translate your high-level language application code to machine code so that the hardware can execute it. And the second component is operating system, or it will do the service for all the application software as well as hardware. So it will handle the input like your keyboard or mouse, microphone, and so on, and outputs like your display or headphone. It manages the memory and storage. It will schedule tasks and share the and control the resource sharing in your hardware so that all your applications and other service can work together. Under that, we have hardware. It includes processor, memory, and input-output controllers. So here is the levels of your program code. At the highest level, you have a high-level language, or HLL. It will be written in some manner that close to human language. So it has a level of it is a level of abstraction which is close to the problem domain, and it provides it is provided for productivity and portability so that you can easily understand and can be reuse them many times. Under that, you have assembly language, which will be compiled from the high-level language by a compiler. And the assembly language looks like this. It is textual representation of instructions. Of course, somehow you can understand it, but it will be more difficult to understand than the high-level language. And in order to be executed in hardware, the assembler will compile this assembly language or assembly code into binary machine language, which is a series of 0 and 1 values together. And of course, you are hardly understand this code. However, the hardware will understand and be able to execute this code. It encodes the instructions and data that your program need to do in a CPU. And so your CPU needs instruction set architectures, ISA, and we have two types of instruction set architecture: CISC, or complex instruction set computing, and RISC-reduced instruction set computing. As you can see from the name, CISC will include complex instructions. And as an instruction can do many execution inside, many operations inside, so you need less instruction for your program. However, one instruction would take more time to be executed. For RISC, it is simple instruction. Each instruction will do a simple task, and so you will need more instruction per program because you need to combine many simple instructions together to make a complex task. However, each instruction requires less time to perform. Here you can see the example of CISC and RISC instruction set architecture. For example, for memory operations, which add two values inside memory together and store back into memory. For CISC instruction set architecture, you need only one instruction like this. This instruction will load two data from memory into register and then transfer it into ALU, and after the ALU execute, the addition result will be written back to memory. So you can do all that thing in a single instruction. However, for RISC, you need 4 instructions to do the same task. At first, you will need to load the first data from memory into register, then second data load into register, and then provide those two registers into ALU for addition, and then the result from will be written back to one register inside register file. After that, the store instruction here will store back the value in register file into memory. However, each of these instructions will be much faster than the instruction in CISC. Next, we will go to representing instructions. The instruction is called machine code or machine language, and it is represented by a series of binary, or it is encoded by binary value, so that your CPU can understand the instruction and execute it. We will concentrate into LAGVS instruction set, architecture set, instructions. Yeah, and so in LAGVS, each instruction is a 30-bit words, and or in other words, now each of these instructions will be encoded by a 30-bit instruction word. Inside this 30-bit words, you will have a small part called opcode, which is used to encode the operation, and you have some other field for register numbers and address or immediate value that we will go into detail next. So here and here you can see that in LAGVS you have a number of register or called register field. LAGVS has is used in ARM architecture, and it has 32 registers in total. Each register will be 64 bits. The register name are number from X0 to X31, or the X31 will be called XZR. As you can see in this table, you have many general purpose register like X0 to X7, X9 to X15, X19 to X27. Other register will do some specific task or will be used for specific purpose. You have a stack pointer located in x28 and it can be called as SP. Frame pointer or FS in short is x29. Return address or LR, it is x30, and the register x31 will be XZR, which will keep the value of 0 only. And in our program we will need to use all these register together to make the program work. Here the register operands, as I said before, a register in your register x0 to x31 in your register file has 64 bits, or it is a double words. It can be divided into two half words, into two words like this, or it can divide it into 4 half words. Each half word has 2 bytes like this, or you can use the data in your register by byte, which is 8 bits from byte 0 to byte 7. So one register in your CPU in LACVH will have 8 bytes together, or 64 bits. Next we will go to the instruction formats. As you know, in fact we have 6 instruction formats in LACVH. However, I will go into 5 one that we already use in our lab. The first format is R format. Here you can consider it as a register format. The format is shown here. It 32 bits are divided into 5 parts. The first pass, it always be opcode, which takes 11 bits, and then RM 5 bits. This part we can we don't need to care at this time. RN 5 bits and RD another 5 bits. An example of instruction R format instruction in LACVH is this: add x9, x20, x21, which means that value of x9 will be equal to value inside x20 plus with value inside x21. And when you change it into machine code, you can see 5 parts available here. At this, it is 11 bits, showing the opcode of 8. This one, it is RM and it is x21. So here for this, it is this part that we don't care at this time, so it is all 0 here for 6 bits, and then RN here, which is x20, so here 20 is written here, and finally here is 9 for this, or RD. The next instruction format is D format, or memory access format. It also have 11 bits of opcodes stay at the beginning, and then 9 bits address for the offset address, and then the op2 here we don't need to take care about it at this time, and then RN of 5 bits, 5 bits RN, and 5 bits RT. Here is digit, and here is the register that will be used to show the base address. This address is offset address, and RN, the value inside RN here will be base address. And an example in LACVH is LDUR, or load from memory into register, x9, x22, and hash 64. The meaning of this instruction is RT or X9 here equal to the value inside memory that the address is shown by offset address inside Rn plus with the the base address is given by Rn plus with the offset address shown by this address. So the machine code for this should be this one. This is the opcode for LDUR, and here the offset address, that is 64, and this value it is X22, and this is which shows the which keeps the base address inside memory, and this is X9 or the register that will be filled by the value in from the memory at this address. The next instruction format, the I format or immediate format, it has 10 bits of opcodes, and then 12 bits for immediate value, Rn 5 bits, and then Rd 5 bits. An example of an example for assembly code of this format for in LACVH is SI X9 X9 and #1, which means that the value inside X9 will be equal with itself plus with the immediate value 1. So the machine code you can see here, the example for machine code can be seen here. This is the opcodes, 10 bits opcodes for SI, and then here is the immediate value, that is 1, and then here you can see value 9 represented by for Rn or X9 here, and then this one Rd also equal to 9. And then we have a B format or branch format. For this format, it has only 6 bits of opcodes, and the remaining 26 bits will be the branch address. An example in LACVH is BL branch, which means that the value in PC will be replaced by itself plus with the branch address, or this will be the offset from current value of PC. The machine code you can see here. This is the opcode for BL, and then here 26 bits showing the distance from PC to the place that we want to jump to. The last one that I will mention here, it is a CB format or conditional branch format. It has 8-bit opcodes, 8-bit opcode, and then 19 bits for conditional branch address, and then 5 bits for register RT. An example here is CBZ or compare and branch if 0, X12 and assist, which means that you compare X12 with 0. If X12 is equal to 0, PC will equal to PC plus the address shown by the assist label. So the machine code you can see here, this is 8-bit for CBZ, and here is 19 bits for the address of assist, the offset address of assist from PC, current PC, and this is 12, which show for the RT or X12 here. And so using those instructions, for example, for the B format. In fact, for B format, we have a branch, BL and branch this instruction. We can use that instruction for procedure calls. What is the procedure? The procedure or the function is a subroutine that performs a specific task. It is used to structure programs, and it makes the code easy to understand, and it allows the code to be reused. You can, for example, you can write a procedure called swap, and you store it somewhere in your memory, and after that you can give the input to the procedure and then call to procedure by BL instructions, and your program will run to this procedure and execute it until the end. It will give out the result of the swap function, and then it jump back to the location that you call the program, so that you can use it many times from everywhere in your program. And in order to support for procedure call, of course we need the call instruction BL, procedure label, which means jump and link. The procedure call instruction will execute by putting the current the next PC or program counter into X30. As we know that X30 is a special purpose register. It can be called LR link register. It is used to store the value of next program counter, so that you can come back to that instruction after you execute your procedure. And after you store the value of PC into X13, you will jump to the target address or the address shown by procedure label. And after you do the procedure call, you need to return from procedure by this instruction BR LR. This instruction will take the value inside X13, inside X30 or LR that you store before you call the procedure, and then it write back to a program counter, and so the program counter knows where it should come back to continue your program before calling the procedure. Of course, we also know about stack. Especially in procedure call, we need stack. Why we need stack? It is because the number of registers in our CPU is very limited. We have only 32-bit register, and so you can't use share those registers to too many tasks and too many procedures, and you will need to store those values into memory sometime to release the register for other task. And so you have a stack. Stack will count from the upper address down to the lower address, while your program will start from lower address and count up to the higher address. Your program and your data will start from lower address and count up to higher address, so that you don't have stack will count down and your program will count up. It prevents stack to conjunction with your data. And you have the two tasks or two operations with stack: push and pop. Push will write your data from a register into a memory shown by stack pointer. And you also need to reduce the value of stack pointer by 8 to show the location of that value, that data can be stored into stack. Why you need to reduce stack pointer value by 8? It is because your register is double words or 8 byte data, and so you need to reduce for 8 bytes because in your memory data is counted by byte. Another operation with stack is pop, or it will take element from the stack. In order to pop data out from stack, you will read the data out from stack from the memory shown by stack pointer, and then you increase the value of stack pointer by 8 to jump back to the next data that you can take it out from stack. And stack is a kind of last in first out data, in which the last data you push into stack will be taken out first. And so for addressing mode, as you can see in your instruction formats, we have a number of address mode. Here you have 4 addressing modes. The first addressing mode is immediate addressing, which shown by the immediate value inside your instruction. And you can see this immediate addressing mode in your I format or immediate format, instruction format. The second addressing mode is register addressing, in which the a value will be given in your instruction, and that value is the number, the name of a register, and the content inside that value, the value inside that register will be used, and it is called register addressing mode. The third addressing mode is base addressing, in which you can see in memory load or write instructions or deformat instruction. You will have an address given in your instruction together with a register which keeps the base address inside your memory, and so you need to add the content of that register together with the offset address, and then you will have the address in memory that you would like to access, and that from that address in memory you can take out a double word or 8 bytes into your register, and then you can use it as double word, as word, half word, or byte. The fourth addressing mode is PC relative addressing mode, in which you can see in the branch or conditional branch instruction format. You will have an address given in your instruction. That address will be added together with PC or program counter, and so you will have a new address, and that address will point to a location in memory, and you can read out a double word from memory after. That's all for our summarize today. in this video. Thank you very much.